In the previous video, we were talking about synchronous transfer and asynchronous transfer. Okay, there are two different methods of data transfer, which are stored method and the handshaking method. Okay, now in continuation to that, there the data can be transferred either serially or parallelly also. Apart from being synchronous or asynchronous, it can be transferred parallelly or serially. Now, what I mean by parallel transfer? In a parallel data transmission, each bit of the message has its own path and the total image is transmitted at the same time. Say for example, if the data, if a character has to be transferred and the character has got 8 bits, then there will be 8 lines in parallel data transmission. There will be 8 lines wherein the 8 bits will be transferred parallelly with each bit in one line. So 8 bits all at a time will be transmitted to the destination all at the same time. So this is called parallel data transmission. Now what is serial data transmission? Serial data transmission is it will be transmitted each bit by bit. Okay, so there will be only one line. So it will be transmitted one bit at a time. So that is called serial transmission. So parallel transmission is faster because the 8 bits can be transferred at a time, all at a time, but it requires many wires because if the data transfer rate is say 8 bits at a time per second, 8 bits per millisecond, then what happens is it requires 8 wires. If it is more, then it may require more number of wires. So because of that, it will become, when wires are more, it will become, the circuit will become very clumsy. So that is why parallel transmission is used in short distances, okay, where speed is very important. Whereas serial transmission is very less expensive because you require only one single line, and but even though it is less expensive and it is slower also. So this is about parallel transfer and serial transfer. Now this parallel transfer and serial transfer can be synchronous or asynchronous. So what do you mean by synchronous serial transmission is serial transmission, the two units share a same clock. Okay, we already know that in synchronous data transmission, there will be a common clock shared by two units, and then so this is the transfer between the two units will be synchronized by the clock pulse. So we have already seen that. So this is it's a synchronous, but it's a serial transfer where the data is not transmitted all at a time. It will be transferred one bit after the other. So that is called synchronous serial transmission. In long distance serial transmission, there won't be a common clock. In a short distance serial transmission, there will be a common clock which is common to both the units and synchronizing the data transfer bit by bit. Whereas in a long distance serial transfer, each bit will have its own separate private clock pulse. We also private clock generating the clock pulse. So each unit will have its own private clock, and there will be some synchronized signals will be transmitted so that to keep the clock pulse of both the units synchronized. Okay, so that is serial transmission, synchronized serial transmission. Whereas what is asynchronous? Asynchronous serial transmission is the in when in synchronous transmission, the point is, since both the units, the clock pulse has to be synchronized for both the units. So what happened, and the clock pulse is a continuous one. The clock will generate pulses continuously. So data has to be transmitted continuously between the two units in order to keep up with the synchronized clock. Whereas in an asynchronous data transmission, only when the data is available, the data will be transmitted. When the data is not there, it will not be transmitted. So the mostly asynchronous transmission is used, and that too asynchronous serial transfer, because we saw that in serial transmission is less expensive, but even though it is lower, it is less expensive. So asynchronous serial transfer is mostly preferred. Now, how does asynchronous serial transfer take place? So we saw it is asynchronous, which means there is no common clock which synchronizes the data transfer. Okay, and it is a serial transfer. What do you mean by serial transfer? All the data bits are not transmitted at the same time. It is transmitted one after the other. So which means the two special special bits are attached or inserted at both the ends of a character code. If a character has to be transmitted from one unit to the other, then there will be a start bit which is attached at the beginning, and there will be a stop bit which is attached at the end. In between these two bits, this start bit and the stop bit are the special bits which are attached, and in between we have the data bits. So the transmitter rests at the one state when no characters are transmitted. So that is the convention that is under assumption. Under assumption, the assumption here is that always the transmitter will rest. The transmitter will rest in the sense there is no data for it to transmit. So that is why the transmitter will rest at the one state. So initially the transmitter will be, if you look at the timing diagram here, the initially we start off with a 1. Okay, so the pulse is a 1 pulse, so which means the transmitter is resting. There is no character to be transmitted. Then whenever there is data for transmission, it first initializes with a start bit. So the start bit will always be a 0. Since the idle state represents one represents idle state, so now the start of a data transfer will be identified by a 0 bit. So the start bit will be 0, and then there will be only one bit which is a start bit, which is always a 0. Then followed by that you have 8 bits which are the character bits. So you have 8 bits here which are character bits. Then followed by the stop bit. Stop bit is again either it might be a once the stop bit will again be a 1. Okay, the start bit will be a 0 and the stop bit will be a 1. This one, there may be 1 or 2 stop bits also. It is a start bit alone, there will be only one single bit, whereas a stop bit can be 1 or more. Okay, so this is the format in which the data will be transferred in asynchronous serial transfer mode. Okay, so these are all the rules. So when data are not being sent, the line will be kept in the one state. Okay, idle state. Then the initiation of a character transmission is detected by a start bit, which is always a 0. Then the character bits always will follow the start bit. Then after the last character, a stop bit is detected when the line returns to the one state. So there will be at least one, one bit, one stop bit, or even more than that. Okay, so the receiver knows in advance the transfer rate of the bits and the number of information bits to expect. So what is the transfer rate of the bits and the number of information? Okay, how many characters, how many bits in one character, and how many characters are to be transmitted. So this the receiver will know in advance through a control command. So this is the format in which the asynchronous serial transfer takes place. And what is the baud rate? The baud rate is defined as the rate at which the serial information is transmitted and is equivalent to the data transfer in bits per second. What define baud rate? Baud rate means the number of the data, number of bits transferred per second is called baud rate. Okay, so we will see the block diagram of asynchronous serial transfer. Now, this block diagram we have already seen. When we saw the I/O interface. So it's exactly the same diagram, but except that there are this portion there we had port A, port B registers, and then status register and a control register. Okay, so the same thing we are having here, except that this portion is now elaborated, slightly modified to incorporate the receiver and transmission, asynchronous serial transmission, transmitter and a receiver. So it's a universal block diagram. So here we have the bidirectional bus and the bus buffers, and we have the internal bus, which we already had in the previous block diagram also, and the timing diagram. This is the chip select, and then you have the register select. Okay, there, and then we have IO read and IO write. Okay, the read control and the write control. So RS here, there we had RS0 and RS1, two controls, and then based on uh, you know we had it's almost the same, but here he has just given register select. There, register select is a combination of two bits, RS0 and RS1. In the previous diagram, there were two register select bits. Here it is just for simplification, it is just given RS. Okay, CS is chip select and RS. So whenever CS is 0, this interface is not selected. Whenever the CS input is 1, then this particular interface will be selected. And then if you see RS input is 0, so 1 0, and the operation is a write operation. Then the transmitter, this transmitter register is used for write operation, and the receiver register, okay, will be used for the input operation, read operation. Okay, so what happens actually is, whenever a write operation has to take place, so the data is available in the data bus. So what happens is, first of all, this interface is selected by giving appropriate signal in the chip select. Okay, and then the register select. So here, since it's a write operation, this transmitter register has to be selected. So appropriate signals will be given here for CS, RS, RD and WR. So the appropriate signals will be placed here. So the signal in CS will select this particular interface. Then RS will select a combination of CS and RS, and WR, right, will select the transmitter register. CS, RS and RD will select the receiver register. Okay. Then, so what happens is, first when the write operation has to take place, then the transmitter register has to be chosen. So the corresponding signals here for CS, RS and WR will be given, and the data will be available in the bus buffers. So initially the CPU has to first ensure that this transmitter register is empty. Okay, if already some data is being transferring, in the previous data is still there, and it should not, by mistake, it should not place the new data on top of the old data. So for that, it just makes sure that transmitter register is ready and it is empty. So for that, it issues a status command. So the status register will say whether the transmitter register is empty or not. So based on that status command, once when it comes to know that the transmitter register is empty, so it places the data in the bus buffer. So what happens is, from the bus buffers, it gets transmitted to the internal bus, and from internal bus parallelly it goes to the transmitter register. Okay, serial transmission does not happen here. It happens only at the end. It happens from the shift register to the final IO. Okay, so there only serial transmission takes place. But here, in between transmission between internal bus and the transmitter register happens parallelly only. Okay, and then from transmitter register, this is again a temporary register. So a transmitter register to what is called a shift register. So shift register is one. For every clock pulse, it was either a left shift register or a right shift register. So this here, it will be a right shift register. So what happens is at for every pulse, the bit number of the bit stored in the shift register will be moved one position to the right. That is called as a shift register for every clock pulse. So that is what we want. In a serial transmission, only one bit can be transferred, one bit can travel, and one bit by bit only the data can be transferred. So that is why we have a shift register here. Okay. So from the transmitter register, the data gets transferred to shift register bit by bit, and from shift register, it gets transferred to the IO device, the external device. So this is the transmitter register. Now, similarly, whenever a read instruction has to happen, so the reverse will take place. So what will happen? This particular CS input, RS input, and RD input will be given. Okay, so corresponding signals will respective signals will be given, and then the status again will be the CPU will check every time, it will check the status register whether the receiver register has got some data. So whenever there is a read instruction, so the data has to come from, let's say, an input device. So let's say a keyboard. So what happens? Data from a keyboard will directly come into this receive data through this SIG. Through these lines, it will come enter into shift register. Again, this shift register will be a left shift register. So for every clock pulse, the data in the register will move one position to the left. So every time the data, it is just like pushing the data one by one bit after another bit. So the data will be pushed into this shift register, and from shift register the data will go into this receiver register. Once when data goes into the receiver register, the status bit will be set saying that the receiver register has got data. So the CPU will keep checking the receiver register to check whether the data has entered the receiver register. Then through the status command, then it will issue an input command, and from there, from receiver register, parallelly data will enter into the internal bus, and from there it will go into the bus buffers, and finally it will reach the CPU. So this is what will happen. This is a sequence of instructions that will happen, that will take place for an input instruction. Okay, here I have given the same thing here, and before any transmission takes place, the control register bits, control instruction will be issued by the CPU to define the baud rate. What is the baud rate? Just now we saw the definition for the baud rate. The baud rate is number of bits have to be transferred per second. So the baud rate, what is the baud rate? And number of bits in each character. Okay, so which means for each character, we saw that if it's a 8-bit character, along with that 8-bit, two other bits will be sent. One bit will be a start bit, and the end bit will be the will be attached. The stop bit will be 1. That will be attached. So only when the number of bits in each character is known, then it can identify the start bit and the stop bit. Otherwise, everything will be in zeros and ones. How do we distinguish between the start bit, stop bit, and the data actually? So the number of bits in the character will be predefined, will be known beforehand. Okay. So the baud rate, number of bits in each character, and then whether to generate the and check the parity. What do you mean by parity? I told you parity is even parity or odd parity. Even parity means the number of ones in the data. Okay. Well, say let's say if you take up this, this is the data 11000101. Count the number of ones here. It has 4 ones. So 4 ones means it is even parity. It has got 4 ones. So if an even parity is set, then it will say that the data contains even number of ones. So it will count the number of ones and check whether the number of ones is even. If it is even, it will assume that the data has been transmitted correctly. Otherwise, if an odd parity is set, it means the number of ones will be an odd number. Okay, so mostly even parity will be followed. So the control, the CPU through its control command will tell the interface, the peripheral controller, as to what is the baud rate, how many bits each character contains, and then whether the parity is being generated and what type of parity is it, and number of stop bits. I told you the number of the stop bit can either be a single one or it can be more than one, one once, okay, more than one once. So how many such stop bits are attached to the data? So all these things are predefined, and it will be informed to the to this controller through the control command. Okay, through this peripheral controller, through the control command by the CPU. So all this will be known. And then we already know that the status register contains IO flags which will tell whether the transmitter register is full or empty. Similarly, receiver register is full or empty. And if there is any error, I told you about the parity error. So whenever a parity error occurs, so the status flag will raise the error, and then it will tell the CPU will also be checking, or after the transmission it will keep checking whether such an error has occurred. Okay, when an error occurs, the data will be transmitted again so that the receiver gets the correct data. The destination gets the correct data. Okay, so this is about the asynchronous serial transmission, and this block diagram is a common asynchronous communication interface.